Let's go. All right. LibGMP. Okay, so what's the deal with LibGMP? The first thing to do with GMP is to check out the website. And so, official website is here. There's probably Markdown shortcuts. I don't know if they are. Okay, and basically, what does it say? We'll do a block quote here, and it is GMP, which stands for GNU Mixed Precision. GNU is the recursive acronym for GNU's not Unix, right? Is a free library for arbitrary precision. What does that mean? Arbitrary precision means of any size. Python has arbitrary precision algebra, or computation, I guess. The C programming language does not, and we've demonstrated this. Can I make this bigger? Is that better? That feels better. Okay. So let's decompose this. G is GNU, or GNU is not, or yeah, GNU's not Unix. It is the free and open source Unix ecosystem. Includes GCC, glibc, others. Generally considered an essential component of the Linux ecosystem, right? There are a few, specifically Alpine. I think Alpine is not GNU Linux, right? MP, mixed precision. What does this mean? Integers have no fixed size. That means, well, we'll call them ints. Ints have no fixed size. Therefore, is there a, therefore, can I do that? What's that look like? Yeah. Therefore, not necessarily any maximal value therefore not necessarily finite, and therefore may be regarded as integers. Of course, you can't put actual integers in there. You can just treat them as integers. Okay. It works on signed, rational, and floating point numbers. Do we care about those? No. We only care about integers or signed integers. And naturals or unsigned integers. On RSA. That's so large. That's huge. How's Markdown work? Looks so goofy. I thought it'd be this size. I don't know how Markdown works. Okay. Silly. Okay. Well, we should do it this way. And naturals. On RSA, most arithmetic may proceed unsigned. Critical arithmetic is very challenging without signed values. And specifically, we're going to be doing modular arithmetic where remainders can be negative. And so you don't have to treat the remainders as negative, but otherwise you have to be doing everything modularly. If we're using LibGMP, we're not doing things modularly unless we're implementing the modularity manually or as our own implementation detail. So either you're dealing with signs or you're dealing with modulos. Signs and modulos are the same thing with finite values, right? Okay. There's no practical limit to precision except the ones implied by the available memory. This is one of our first mentions of memory. One of our first mentions of available memory. Why does this matter? We have thus far written memory safe code, not intentionally, but by not introducing memory management. LibGMP introduces memory management. In a way. Okay. So, and we will title this heading on LibGMP. And having introduced that, let's go ahead and begin hacking. Okay, so let's say the first thing we need to do is, I guess we need to make a container file. Vim container file. What needs to be in here? We need to say from. How do you make container files? Let's see, what do I have here? Ooh. Oh wait, do I already have one? That doesn't help at all. lsdev crypto c89 container file. Just cat this from Ubuntu. We'll make one of those here. Let's go through the steps of getting this to work. And we're going to cat container file. Start with this for now. I'm going to grab this and I'm going to put it in a markdown document. Usage. We will begin with this container file. Can I do like IAM equals container file? Does that work in base markdown? No, it does not. Okay. Okay. So let's go ahead and do we have a container file? Yes. I don't know what a.out or macros.c is. Oh, it's probably helping a student. Okay. So we've got our container file. I'm just gonna work at home because like what else am I doing? Podman build t. We will call this libgmp dot. So we'll build the image. That does not look too slow to me. Oh, I don't know where to see YouTube comments. Huh? I'm watching Discord. That's fine. That doesn't affect me. Okay. We have libgmp here, so we're going to podman run it libgmp. There we have it. This is bash as printing things, right? Okay, so we're in here, and at this point in time, I think it's time to start doing some GMP development. And to begin that development, I'm going to introduce, and I think I can find it here. There's a famous-ish, I guess. I'm typing in another screen. I'm Googling. Gosh, where is it? GMP. Right, the tutorial on GMP. The tutorial on GMP. We will follow this tutorial. I don't know why it took me so long to find that. This tutorial is going to begin by giving us basically a series of C programs. It's not too interesting. I'm not actually going to show it to you. You can click through it if you want. But the motivating example here is that factorials get too big too quickly. I'm going to rip some factorial code, and we'll just look at that for an example. So we're going to come back over here. What are we going to do? We're going to create something called factorial.c. We're not going to call it that. We're going to call it fact.c, dim fact.c. We'll drop that in. What is this doing? We have a factorial function. I think I'm allergic to comments here. I don't think I want an assert statement. These are all using ints? I guess it's fine to use ints. This code style, right? Like, this is like missing spaces that I'd like, but other than that, I think it's fine. We're going to check if the user has a command line argument. We don't need our code to work. Take that out. There's A to I, which you've seen. Oh, how do I undo? There we go. I'm going to get rid of the assert. Okay, so this is a factorial function. For some reason, it's returning 1. Don't love that. I think that probably works. Is there an open line at the top of this file? Yes, there is. Okay. Cat fact.c. There's the factorial.c, and we'll put this in the Markdown document. We will first use this file. Okay. What's over here? Oh, there's so many empty spaces in it. I don't know that I can tolerate that. Hold on, sorry. Remove. I want to do this. Insert here. I'm not super good at cross-line deletions yet. Delete some lines. I guess I don't need to write C89 right now. Let's see. Okay. Does this thing actually compile? Yeah, okay. Cat fact.c. Excellent. So is there an empty line at the end of the file? That looks like it. Yep. There we go. Make a slightly smaller footprint. For me, on my brain, more so than like on the file system, right? Okay, so there's our file. Okay, what are we doing here? GCC fact.c. Okay, and I'm advised to I gotta do an output. We'll call it fact. Okay, so if I do fact, that's segfault because I removed the error handling code. That's 10 factorial. What is 1 factorial? Right. So we have a variety of factorial options here, right? And why do we use factorial? To motivate arbitrary precision, because factorials get very large very quickly, right? So this is an easy way to get up to the size of values, the 2,000 to 4,000 bit precision values that are used for SHA or for RSA keys, right? No such thing as an SHA. And so let's work with that. Put 10 in here and put 20 in here. And already at 20, we've noticed we have a problem. What this is suggesting is that this is suggesting the factorial, which is the series of multiplications, should be returning a negative value, and that's not true. And we can do that by implementing factorial in Python quickly and testing it. So I can not use Python because I didn't install it in this image. Or wait, is it because I didn't use Python 3? Oh, there we go. Okay. So lambda fact, nope, fact. Lambda, let's see, we used n equal, nope, colon. So factorial is n times fact of n minus 1 if 10 else 10. Is factorial 1, 0? No. Fact of. Oh, probably else 1. That looks like factorial to me. Is 10 correct? 3, 6, 2, 8. Those agree. And then we just throw in 20 here and we see, oh, that's not a negative number, right? So we can check versus Python. We can evaluate this versus Python. We find that C factorial of 10 and I factorial of 10 are both 3, what was it? 3628800. Well, 3628800 decimal representation. And then C factorial is 20 is negative. Can I copy paste? Is that possible? I don't know. Yeah. Pi factorial of 20 is positive. It's fun that factorials are 0 terminated in any base system, right? Because you're always multiplying by that value. Right? So this is necessarily contains a 20 times a 10 in it, right? So there's necessarily 2 zeros there, or from other sources. So why is that? As you know, we're working with finite numbers, right? So how are we going to deal with this problem of finite numbers? And the way we're going to deal with this problem is we're going to introduce GMP. We can check to see if we have GMP installed. It's not present by base, so I think I can say what? Locate libgmp, libgmp.a, and I don't have locate. But let's go ahead and introduce sort of the steps and operations we go through to do arbitrary precision arithmetic, right? And it's not graceful, it's not illogical, right? It's just kind of odd. So we're going to do vim fact.c. We're going to include gmp.h. When we include gmp.h, geez, is there just a GMP quick start guide? Might that be easier? Oh, there might be. I expected to see things here that are not present. So I'm going to grab the CUBolder GMP script. Okay. And let's look through this quickly. Oh, did I insert something at the end there? Okay. How long is this file? Jeez. Okay. We're not going to use asserts. Okay. So what is this? We have a character input buffer, so we can type in numbers that are up to 1024 decimal characters wrong, like, and that is going to be much larger than 4096. Well, not larger. That is going to be larger than 4096 binary characters, right? We are introducing a special term here. MPZT is the type defined for GMP integers. You've already seen different integer types. That shouldn't be too alarming. It is a pointer to the internals of the GMP integer structure. So we are once again having to deal with pointers. An MPZT is not a numerical value. It is an address of a data structure that represents a numerical value. And we do not, as clients of the system, know the internal manner in which that data structure is maintained, and we avoid interacting with it. So, what are we going to do? We are going to instead only use built-in GMP operations, which are documented the same way any other API is documented. We're never going to work with MPZT directly, okay? So we're going to provide it as arguments to functions. Those functions are going to be prefixed with MPZ. And that stands for mixed precision integer, Z for the integer, right? So we've got some flags. We're going to enter a number, scanf. This is telling you that I told you to write in secure code. That is true. Who needs comments, right? Let's see. Nope, that's not what I meant to do. How do I go to the end of words? There we go. Okay. So the first thing we're going to do, okay, so we're scanfing, right? We're familiar with scanf, I believe. I'm going to regard us as familiar with scanf. After we scanf, we're going to initialize the number. This is interesting, right? So we've discussed the notion of initializing versus uninitializing things. Similar enough to initializing a NumPy array, right? So we're gonna take two stages. We're going to direct the GMP library to take our MPZT we've declared and connect it to the internal data structure, right? This is similar perhaps to initializing a class in Python, right? They're similar enough to objects of classes. We are going to take GMP, or we're going to take the mixed precision integer, the MPZ, which we have named n, and we are going to set its value equal to 0. Now, one thing to look at here real quick. My hands are not on the keyboard. Okay. I said this is similar enough to objects, right? And it is in a way, right? But you'll notice we're not using dot notation, right? MPZ set UI is a function. It is a function where we disregard the return value, which is reasonable, right? We can cast the return value. Right? We can say we do not care about the return values of these things. In fact, we don't, right? And this is a way to denote that. Rather, it's not a pure function. It's a function that has some side effect that impacts the memory of our system in some way. So after MPZ init has been called, a data structure exists. And after MPZ set UI has been called, the data structure knows that it is supposed to be representing the value 0. It is not the value 0. It is representing the value 0. In the same way, the ASCII 0 character represents the value 0, but it's not equal to 0. We can do the same thing. Okay. Now we're going to take our input. We're going to parse it as base 10. And perhaps I want that to be base 16. I'm not going to overthink it. Okay. And we're going to remove the assert statement because I don't believe in writing code that doesn't contain bugs, basically. Okay. After we've read in n, we are going to print out n using MPZ out string. Fair enough. We could also here at this point convert it to hexadecimal, right? And then what are we going to do? We are going to use an MPZ add. Now there's more than one MPZ add, and the reason there is more than one MPZ add is for a very specific reason, which is that we don't always want to be adding mixed precision integers together because we don't have a way to type mixed precision integers into the computer gracefully, right? So MPZ add UI stands for MPZ add unsigned integer. So what is going on here? We have an MPZ, and an unsigned integer. And this represents that n equals n plus 1. So the MPZ library is going to take n. It is going to add 1 to n. and it is going to store that value back in n. So these two values don't have to be the same, but they kind of have to be the same for us because we've only initialized one MPZ, right? But this could just as easily become I, right? Then we would have an I here, and we can't do that because we haven't made an I. But you can play around with this and hack with it and get it to work on your own. We're going to add 1. We're going to get out of insert mode. We're going to delete a line. We're going to say n plus 1 equals something. What is going on with the indentation here? So look at that. This is unrelated, but this operator, it's not really an operator, right? This symbol, it's not quite an operator. It has spaces on both sides, right? This one has a space before it and then not a space here. I don't love that, so I'm changing it. Okay. We print out the MPZ, and then we're going to print a. We can also square the value by taking the multiplication. I hope that is as you would expect, right? There is definitely a. Okay, so what I perceived as typos are intended. I don't know why. I would not want to write my code this way, and that is okay that someone else writes it that way. Okay, so now I have these spaces around the arithmetic symbol. And then we print that to standard out. Okay. Ooh, what all is going on there? How do you go to, what's end of file in Vim? Shift G or something? I want to delete the rest of the file. I want to do D shift D. Okay, that worked. Okay. What is this? MPZ clear. Well, the MPZT, we initialized it, and when we initialized it, the GMP library made a series of agreements with the operating system to control some aspects of system memory. We will learn more about that at a later date. That's what's going on. We know, but GMP does not know that we are done working with it, right? GMP is responsible for retaining n until we say we don't need it. Now we don't need it anymore because we're about to return from our program, right? So we signal to GMP that we are done with the value. Then GMP will stop maintaining the value. Then the operating system will stop maintaining the value, and that memory will be freed up for future use. When we use memory in a device, we should always make sure when we are done using the memory, we specify that we are done using it. Otherwise, that memory will not necessarily become available again for use, and we'll get performance degradation over time. I'm going to return 0, 0 to denote non-error exit status. I am surprised there was not a return 0 here, but there was not, and that is all right. Different people write code different ways. We're going to save this value. I have a question. Okay. Let's look at fact.c. I could have void cast all of these. We can debate the merits of that. We implement a factorial using the MPZ_T type supported by the GMP.h library. Is that correct? So here this is. And we will come back over to our terminal. Go to GCC, fact.c. And we will see an important error, and this is an important and worthwhile error to deal with. GMP is not present on our system by default. This is an uncommon usage of computers, the C programming language. Frequently we do not need numbers larger than 2 to the 64th for anything, right? That's a very large number, right? So perhaps if you're using a system for scientific computing, of course then you need larger numbers than that, right? That's 2 to the 64th is much smaller than the number of stars in the universe or stars in the galaxy or pounds of granite on Earth or anything else, right? And so certainly there are cases where we need these larger numbers, which is why there's a library, but it is not a default case to need these larger numbers. And in fact, frequently we go throughout our entire lives and never use a number larger than 2 to the 64th, right? So how do we solve this problem? Well, we're going to have to install GMP. And I think if I just type apt install GMP, that's not what it's called. And so I solved this problem. I'm Googling how to install GMP on, I think I'm on Ubuntu here, right? And I just went to Stack Overflow. No, I went to Ask Ubuntu. I'm on a Stack Exchange called Ask Ubuntu. I guess I don't know what that is. Anyways, I'm gonna like it. When we try to compile, we yield the following error. What is the error? It says, I'm not getting it? Yeah. We need to install GMP. I just looked it up and found this. That's not what I found. Please copy paste. Okay. Found this. And what does it say? It says sudo apt get install libgmp3. On containers, we do not use sudo. We use modern Ubuntu with apt instead of apt-get. And when I say modern, this answer was posted in 2012. So that is 12 years ago of package management. Considerable developments have taken place since then, so I am going to say apt install libgmp3. Did you say dev? What's it dev? Going to... Oh, I don't have built-in copy from my Markdown. I don't know how Markdown works. That's fun. Oh! I'm going to use /y because I want to. Did not lock. I may have played myself. Move var lib package lock front. Fair enough. There's some way to deal with this. Oh wait, do I need? And the way I'm going to deal with this is I'm going to update my container file. And I'm going to put libgmp3 dev in there. And then I'm going to build it. Podman build libgmp. Am I doing this right? libgmp dot. This shouldn't change much. Well, it looks like it's working. So now we're going to podman run. But we should podman. Okay, do I have like a bunch of feel like I should get rid of all of those. I wonder what I was doing. Podman. System print. Yes. Okay. I don't know why I did else. Podman, peace. Okay. Podman, run IT. So that is run with an interactive terminal. Where we're going to run the LibGMP image. And we don't have factorial. Not to worry. I have a factorial saved over here. Enough. Cat fact.c. Very good. GCC fact.c. Fact. Ooh. What's going on here? Well, this is an interesting and novel and distinct error, and let's document it. I simply updated my container file. Oh, I should have grabbed the usage. Okay. We're entering a new stage, which is compiler class. So here's the problem. I have GMP.h on my system. That's why I'm getting a different error, right? But there's a bunch of mixed references, undefined references. This is the same reference we get when we write a function that is undefined. I can demonstrate that quickly. Do I need to demonstrate that? I don't think so. I don't think that's a use of time. So if you write a function, if you refer to a function that isn't defined, you get the same error. That's an undefined reference. Right? You may get the same thing with variables. And so GMP.h is present on the system, and GCC can see that. But it can't see the implementation of the functions I'm using on the system. And in order to do that, I have to do something novel, something I think we haven't done that much before, where I'm going to provide a compiler flag that isn't going to restrict the power of GCC. So we've seen things that restrict the power with standard C89, for example. We say, hey, yeah, I need you to only use things within this smaller universe, right? And I think C2x gives you more power than default, perhaps. We're going to do something different, which is we're going to use a flag for a library. The most common one I'm familiar with is library math, which I am pretty sure when I used absolute value the first time I had to include that flag. It seems like maybe you don't anymore. But we're going to use LGMP, the library GMP. I think this is going to work, and it did. And we can see other things that happen. You have to get the name right. I could not tell you how you're supposed to figure out. You're supposed to say apt install libgmp dev3 without Googling it. Maybe that's wrong. Is that not what we installed? Oh, it's a libgmp3 dev. Yeah, so you're just supposed to know that's what GMP is called on your system. And then you're also supposed to just know that GCC expects LGMP to be the name. So it's called libgmp3 here. It's called LGMP there. And I think it's called something else on Alpine. Maybe just GMP dev. Alpine users should go look into that and let me know what you think. Anyways, where is it? This thing compiles without error. Fact works. We can do 10. And we can't do 20. Yeah, it only runs once. We're not really taking factorials yet, right? But we can get to very large numbers. What's a number that's large enough? So that's to the 16th. That's not that impressive. I think I was I get 1,024 characters, and an easy way to write something with that many characters is to do 10 specific characters some fixed number of times. So we do 2, we can do 3, 4, and I can start with 5, 3, 4, 5, 6, 7, 8, 0. We started with 5, so I can, and you just look for zeros, and you see the number after 0, 6, 7, 8, 9. And so this thing is 100 digits long. So it's approximately Google. We gave as an example of a number. No problem at all for GM. Something interesting to point out. We can take the length of these values. I don't know if you're supposed to be able to copy paste in your terminal like this. It always feels like cheating when I do it. Interesting thing going on here. Sure, paste anyway. Yeah. What'd I break? Oh, I didn't. That's not what I meant to do. Len of that. When I square numbers of size 100 digits in any number system, these are decimal, I get numbers that are up to twice as large. And one of the other interesting ways to do this is we say product equals some value. Say prod.bitlength, which I can type. And then we can also do, what are the things that are not products? Factors? Oh no, we're using factor and factorial. Okay, and then we have this one. Terminated string liberal. What is? Oh, I'm highlighting the line. So as say factors equal this. That's not right. That is definitely not right. There it is. Okay, and then we can say f.length. Length is 330 bits. That's 653 bits. So in base 2, it's also twice as big. How do I leave Python? Okay. What's the usefulness of all this? Well, on 4096T, ask for some very specific things, and I'm just going to go to the crypto repository, and I'm just going to probably curl some files real quick. Okay, so let's do this. We're going to curl. Oh, that's not what I want. That won't work. Oh, I don't have curl. Rookie mistake. Large. Okay. And then we're going to do the same thing with tester. Copy name. Curl. Okay. Let's do vim tester dot. Let's look at this thing real quick. Okay, so what's going on here? A lot of nonsense, right? So I use the boilerplate to only run this thing if it's invoked directly at the command line. So if you include it by accident, none of the stuff runs, but you have access to some values, right? I use subprocess and OS. Why do I use that? I'm using this to run a variety of scripts, and I'm going to highlight some text now with my mouse. So we're going to see elf file name, executable load format. And so I'm going to use the built-in subprocess library in Python. I'm going to run a command. Subprocess is incrementally more stable than os.system. I don't know why. I just told to use it. I didn't look into it. That's not part of my interests. We're going to use gcc ontester.c with 4096t as the input file type. This is the thing you're supposed to do for the homework. We're going to use all of our flags that we use to make sure that we don't make silly goose errors. We're going to use .o with an alpha file. Important to note, this thing will not compile successfully if you use libgmp, right? Because it's not looking for the file. So the expectation is you implement 4096t without libgmp, right? There's a variety of checks. Make sure the file exists after compilation. And then it checks the first 4 characters of the file. Is that what it does? I don't know what it does. Checks to see that it exists. I don't remember what this does. Yes, it checks the characters, stores them in result, and makes sure that the elf file says it is an elf file. And the first character before elf is like something else. Then we import the random. We make 2 large random numbers. What are these? These are between 1024 and 1027. And then much smaller. Why is the second one smaller? Because we're going to divide by it. We don't want it to be too big. We convert them to hex. And the reason we convert them to hex is that my hookups affect hex values. This is just a way to use the various built-in add, subtract, multiply, floor division, and modulo. I call remainder here because we're only working on positive numbers. So modulo and remainder are the same across Python and C when we're only working with unsigned values. And the reason we're going to do that is I am going to make a dispatch table of operations. We're not going to check sub. Don't need to. There's no benefit to it. So, because I provide sub for you. We're going to loop over each operation, add, mul, quo, rem. Post like Python 3.9, this will go in order or something. I think they now keep order unless you tell them not to or something in Python dictionaries. And what are we going to do? We're going to check the output of running the elf file on 2 inputs, 1 and 2, with specified operation add, mult, quotient, or remainder. We're going to use base 16. We specify the end file that is returned by the subprocess. Then we're going to use internal Python. We're going to use the same operation. So if we provided add, we will use Python add from operator add. We will apply add to big 1 and big 2, which are our 2 random values. These are stored as numbers. These are stored as strings, right? And we are going to compare this integer to this integer. And if they're the same, we say it passes. And if they're not, we say it fails. Okay. Go ahead and exit that. What's tester.c do? This includes 4096t.h, which is the thing you're supposed to implement 4096t in. And I have what is going on here. Big to I. X string to integer. I don't know. They're nats. I will allow you to puzzle out this code, but you'll see it's reading blocks of hex. This seems debugged to me. I actually debugged it using the GMP library. We also have a way of printing output. And we also have a way of evaluating. I forgot you can't switch over strings in C, so I just switched over the first letter. So this is add, subtract, multiply, quotient, remainder. And at this point in time, you'll realize that I called it remainder instead of modulo because I was avoiding a namespace collision with it. So, and what's going on here? This is big add. My big adds were implemented differently where I add A and B and then store it in C. So that's why I'm printing the out of C. So I'm in different order than MPZ. And that comes down to different people implementing things different ways. I thought MPZ's technique actually makes more sense to me. I thought this would make more sense to you. But when you start using other people's libraries, you reserve the right to be confused by their design choices. Let's go ahead and do a sort of special implementation of the 4096t homework using, like for lack of a better word, using libgmp to solve the problems. And I personally called mine LibGMP, I think, right? Oh, I need the 4096t heading. Well, find that. Here we go. Curl Please work. Alright, it worked last time. There it is. 496t.h. Okay. This one's not too exciting. Add, subtract, multiply, quotient, remainder. Okay. And I'm going to use GMP to solve this problem. I'm going to make one other change first. Let's go back into tester.py. And I'm going to allow myself the LGMP library. And I pressed enter by accident. Disaster. I think I can probably just run tester.py. Oh, yeah, you have to do Python 3 tester.py. There you go. Message file directory. So let's go ahead and I'm going to copy 496t.h and t496.c. So I have something starting to work with. I'm going to open 496.c. And most of these things I can change. Let's see. I don't need any of these libraries, but I'm going to implement each of these. Okay, so let's go through the process, and I'm going to have ways of doing things over here. So I'm going to solve the big add problem using GMP. Let's go into insert mode. Okay, so what's the first thing I'm going to do? Well, in0 and in1 are both arrays of unsigned integers, and I have to read those in somehow. And I think I'm just going to look at the answer key and see what I did. Do I have it somewhere? Maybe. I can, there's an MPZ import, probably. Let's save this. And MPZ import, surely this won't work. Yeah, minimize system. Okay. So, there exists a function called MPZ import. Let's take some notes. Compile with LGMP. And I think we did gcc fact.co LGMP. Let's save that. Can I find the page where MPZ import is? We will use MPZ import, which has a web page. A lot of text there. And what are these? Set ROP from word data at OP being treated as a string. Count is the number of words read. Order is 1 for most significant byte first and 0 for least significant byte first. Or no, most significant word first. So this is word level endianness, basically. This is byte or int level endianness. I just tried these out until I got it to work. Nails is kind of goofy. That is the bits of each word that are skipped. Sometimes when you're doing arithmetic, you don't use the full word size, so I think Python stores 30-bit integers and 32 bits. We saw this when we saw performance degradation at 15 bits instead of 16 bits in class. So nails makes it easier to read things internally from Python if you're doing that. For all I know, Python implemented all of this internally using LibGMP. Anyways, I just happen to have the answer key over here, so I'm going to tell you how I imported things. Because I did this. I did this after some testing. Just test it out yourself. You know how to test code and get it to work, right? This is what mine looked like. And let's go ahead and write add. Where is my terminal? Okay, so I have an in0 and an in1, and I want to put the result in sum. So I know internally somewhere I'm going to need to use mpz add. mpz add is different from mpz add UI because I'm not adding unsigned integers together. So if I wanted to add 2 to a very large number, I would say, and now, where's my, there we go, mpz add UI, and that would allow me to add an unsigned integer to mpz. I want to add 2 mpzs together. Now I don't have the mpzs yet. I'm going to have to initialize 2 of them, right? And so I'm going to create 2 of them, and I'm going to call them mpzt in 0 is taken, so I guess I'm going to call it mpz1, I should 0 index, mpz1 and mpz0 and 1. And there you have it. Okay, then I'm going to do 2 initializations. Going to mpz init m0, and I'm going to mpz init m1. There is in fact a way to do this in a single line. It is mpz inits m0 m1 null. You provide a null terminated string of arguments. It was confusing. I just tested it, got it to work. We're going to use mpz import. I'm just going to grab this thing. What is s? S is defined in our header file. -1 is something I found out worked. That's the size of our things. Then we have 0 and 0 corresponding to Indianness and the nails. And then our input name is not A, but is in0. 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 That's our input. See if I can remember how to yank things. I'm going to yank. I'm going to paste. I don't know why I got 2 lines. Okay. We'll switch to invert mode. We'll put a 1 there. Do the end of the line and do a 1 here. Can you do that in a loop? Yeah, I mean, you probably should. Probably some way. Okay. I'm going to add these 2 values together. I'm going to take m0, and I'm going to add it to m1. And then I'm going to realize that when I add 2 numbers together in mpz add, the result is stored in whatever the first argument is, which means that the second 2 arguments have to differ. And so commonly we would say something like this, where we say 0 equals 0 plus 1, or we'd say 0 equals 1 plus 0. If we do, for example, we're going to store the output in this is m1 equals m0 plus m0, which is not what we want to do. That's double. So I'm going to use m0, m0, m1. Could you produce a return value? Of course you could. Why would we do that? Once I'm done adding them, there's a handy built-in export. I'm just going to show you the same export on here. That's exactly what I have here. MPZ export is also, let's see how this works. So what's it doing? Let's see, C is probably sum. I have no idea where my cursor is. There it is, okay. Sum. So we're going to load things into sum. We're going to load them. What is that? That is the count P. I don't care how big this thing is. So that's how many bits it kicks back. We are, and 4096T specifically, we don't have to worry about our export size because we always make those things exactly 4096 bits big, and then we can only do operations that are not that big. So because I'm using GMP to implement something that is still fixed size but larger, and it is of arbitrary size, I don't care about how many bits it gives back because I know how many bits it gives back. -1 probably corresponds to this -1. Size of it, UNT corresponds to that size. These zeros correspond to each other. And then we just provide the NPZT instead. And I think once I do all of that, all I have to do is, this is a trick question. Do I return something? No. I missed a step. And I missed a very specific step. I missed the step where I'm supposed to clear or release the memory that corresponds to this M0 and M1. I should do that. And I think the way I can do that is with MPZ clear 0 and MPZ clear M1, and that probably works. Let's go ahead and save that. Cat. There you go. And I think from here I can probably run the tester. Bit of a problem. Did I mean to include standard int? Probably. What are all these errors? A lot of them. Oh, did I not include? I know what I didn't do. I need to include 4096. Include 4096t.h. That's my header file. That includes things like that these things are 496 bits big, and it includes things like the 64-bit type. So surely this will work. Okay. Implicit declaration of built-in function. No problem. This should be expected to me. Why? Because cat 4096t.h. That thing does not include LibGMP, so I need to do it here. Include gmp.h. Doesn't seem that bad, actually. All right, this thing's actually compiling. GCC. Oh, it's expecting. Hold on, cat tester. This is expecting the implementation to be 496t.c. Is that one minus n? Yes, it is. Okay. And so if I just say gcc tester.c 496.c, that doesn't work because I've undefined. Oh, I didn't finish implementing the functions. Okay, we can just do this real quick. These will just all be wrong. I did not know I was in insert mode. Okay. I need to learn visual block mode so badly. Okay. Return 0. There's some way to do this all at once, and I can't do it because Windows ruined my keybinds, and I forgot to fix them. Return 0. Space. Return 0. I'll look correct. Oh, forgot my semicolons. I've been Pythoning. And let's see if this works. Python 3 tester.py. Unused parameters. And I think that's just, we're going to resolve this for now by ruining the tester. And the manner in which we're going to ruin it is we're going to like that. Really? Oh, undo. like it's 3 words. I wonder if that's right. It looks correct. Well, we're at least doing something. And I'm not sure exactly what we're doing, but I'm proud of it, whatever it is. Actually, how close is this thing? It ends with CB. Hold on. We can fix this right now. This is 1, 2, okay, we go above the B and we go up 1, 2, 3, 4, 5, 6, 7 lines. B, 1, 2, 3, 4, 5. That's a D. And that D goes over to a 207, which is going to be right here. That's the correct value, which means all of this is just junk data. That junk data is almost exactly twice as big. We can fix that. Sum is being used uninitialized. We just have to mem set it. And I can do that right here. It is 496 bytes. We're gonna mem set sum. We're gonna put zeros there. We need 496, which is some number of characters. I'm just going to 496 divided by 8. That work? Oh yeah, add passes. Okay, so that's a satisfying library full implementation of big add, and it took 65 minutes. Cool. I stopped checking the comments there at some point because my brain was melting. I don't see anyone talking to me. I hope you're all having fun. At 496t.c. Final, whatever, final file. There you have it. I'll post this summer.